Alright, so in this video we're going to be looking at one-sided limits. I have a couple of quick definitions. First, the limit as x approaches c from the right of f of x is how we read that. Things I want to point out, notice right here we have that x approaching c with a little plus sign above the c, kind of like an exponent. It is not an exponent. It is the way we designate the fact that the limit is only going to happen from the right, which means when we're doing a pattern, we only care about the right side of that number. So for example, if we were looking at the limit as x approaches 7 from the right, we would only need to look at numbers 7.03, 7.02, 7.01. We would not care about the other side, 6.97, 6.98, 6.99, because we only care about approaching from the right. The second definition there talks about the limit as x approaches c from the left. Notice that as x approaching c, and then it's got a little negative sign like an exponent. It is not an exponent. It is the symbolization that we use to signify that we only care about approaching from the left. And so when we create our tables with these types of limits, everything's going to work out the same. It's just we're only concerned with the one side. As far as doing them algebraically, they work the same. You don't have to really worry about it algebraically. It's mainly when you're looking at tables. These are mainly for weirder functions, mainly piecewise defined functions tend to be this way. Absolute value functions, which are piecewise defined functions in disguise, tend to do this as well. And those are some of the examples that we're going to see. So let's jump right to an example of these one-sided limits. And poof, like magic, there's our first example. The limit as x approaches 2 from the left of 6x plus 1. We're still going to evaluate these the same way. I'm going to first try and plug in the number. Because this is not a piecewise defined function, if you plug in the number, you're probably going to be fine, and it turns out in this case, I totally am. By plugging in 2, even though it says I'm approaching from the left, I can still just plug it in. I get 12 plus 1, I get 13. That's going to be your answer. That is the easiest type of problem. We typically don't see these problems even written because they're just not, there's no point to them. You don't really do anything from the left. But I want to emphasize the fact that these limits tend to be, or can be done the exact same way. So now let's take a look at like a real example where we have to analyze this. Alright, so the magic example that just appeared, the limit as x approaches 3 from the left, that's what that little minus sign as an exponent means, of the absolute value of x minus 3 over x minus 3. You're always allowed and should try plugging in the value, but you have to be really careful with absolute value because absolute value is a piecewise function in disguise, and piecewise defined functions throw all of our rules out the door. So be very careful. If you try plugging in 3, though, in this example, you end up with 0 divided by 0, and so that tells us that we're going to have to mess around with this thing. Now, you cannot mess around with a piecewise defined function, and you can't mess around with an absolute value because that's what an absolute value is. It's just a piecewise function. So we typically don't mess around with these types of problems. We just end up going to a table, and that's exactly what we're going to go with here. We're just going to create a table just like we did in the previous videos. So let me throw the table up here for 3. Alright, magically that table appears, and we end up with a pattern that's pretty easy to see. Now notice I didn't go beyond 3 because I only care about to the left of 3. Notice there's no negative numbers here outside of the y value. I don't care about that. But look at your x values. Your x values aren't negative, even though when we look at this limit, it says the limit as x approaches 3, and we see a negative sign, and our brains, because we want to categorize things in the most basic way, instantly go, oh, that means negative numbers. No, it doesn't. It's a symbol that does mean negative numbers in some cases, but in math we have symbols that have multiple meanings, and in this case, the meaning of this is the fact that I'm just coming from the left side of 3, and I'm only looking at the left side of 3. Be very careful with that. Notice where the negative sign is. That's how we know that it means something different. Math is very specific with its symbols and where we put things in those symbols, and you have to pay attention to that. Learning math is like learning a language. Make sure that you understand that language. So now we're looking at this table, and we're only caring about the numbers that are less than 3, 2.97, 2.98, 2.99, and if we look at the pattern, the y values are -1, -1, -1, and so then we have to logically think of what would be the next number in that pattern if we were to continue the pattern, and my guess, hopefully yours as well, would be that the next number would be -1. So the limit as x approaches 3 from the left of this function is equal to -1, because that's what the table says. The table is the ultimate authority. It knows what the limit is by following the pattern. Now, I bring this example up because the next example we're going to look at is very similar to this one. So let me throw the next example up there. Okay, so this example looks very similar to the last one. It's almost identical except for that little symbol after the 3 in the limit. Notice it's now saying the limit as x approaches 3 from the right. Now you might think, well, I already did the one from the left, so this one can't be any different. Wrong. It could be very, very different, especially with piecewise functions, and again, absolute value is a piecewise defined function in disguise. It's very important that you look at the table, so let me get the table up here. So when we look at this table, magically, we've got the values from the right. Notice I didn't look at anything less than 3. I don't care about numbers less than 3. My world doesn't exist less than 3. My world only exists with numbers bigger than 3, according to the green highlight that I have up there. So when I'm looking at this pattern, I see that at 3.03, the y value is 1. I just plugged it in and did the work. At 3.02, the y value is 1. At 3.01, the y value is 1. So if I'm going based on patterns, I'm thinking that the next value is going to be positive 1, and that is the limit. It's positive 1. Now, what I don't want you to think, when we look at this example, we look at the limit as x approaches 3 from the left, and it was negative 1, and the limit as x approaches 3 from the right is positive 1. Oh, it must always happen that way. No, it doesn't happen that way. They could be two totally different numbers. One could be 5, one could be 7. They could be the same number. We're going to talk about the meanings behind these here in a second, but don't put don't try and put any connection to the fact that one's got a negative sign and it had a negative 1, and one has a positive sign and it's a positive 1. This is a coincidence from the one that I picked. Okay, so these are the limits. And one thing that's very important for us that I want to make sure that I state here is an extremely important sentence that is going to help you. It's not a rule. This rule could be broken. This is a Krieger rule, but for the most part, if you follow this rule, everything's going to be fine. So here's the rule. Our rule: one-sided limits always exist. Always. That is a good rule for us. I've taught calculus for many years, and every problem we've ever encountered, this is the case. So keep that in mind. When you're doing a one-sided limit, you're going to get an answer. Now, the second rule, this is a rule in math. This is something that we need to look at as well. When we're looking at this example of the limit as x approaches 3 from the left and the limit as x approaches 3 from the right, my next example that's going to tie together with these two is looking at the limit as x approaches 3. Not necessarily from the left and not necessarily from the right. Just the limit as x approaches 3 of that function that we're looking at. And I mentioned this in an earlier video, and this is something that I definitely need to drive home now that we're talking about one-sided limits. In order for this limit to exist, we have a rule that I want to put up here on our paper, on the whiteboard, or whatever. So let me get that rule up here. Alright, so this rule that I've got boxed here that magically appeared is an extremely important rule. It says the limit as x approaches c of f of x equals L if and only if the limit as x approaches c from the left, that little negative sign of f of x, is equal to the limit as x approaches c from the right, the little positive sign, and that's going to equal the same number L. L is just a number. What this basically says is the only way that a limit can exist is if the left side and the right side approach the exact same value. So when we're looking at our total problem here on the right side, we see that the limit from the left, once again, the limit from the left of 3 is negative 1, and the limit from the right of negative 3 is positive 1. Since those are not the same value, then when we try and do this example of the limit as x approaches 3, that limit does not exist, and we abbreviate that with a simple DNE. And that doesn't exist, and I'm going to put the reason here. We normally don't need to write the reason, but you're learning, and so I need you to understand the reason. That does not exist because the limit as x approaches 3 from the left, there we go, of f of x equals negative 1, and the limit as x approaches 3 from the right of f of x is positive 1, and negative 1 does not equal positive 1, so the limit cannot exist. We do these for piecewise functions and for absolute value because absolute value is a piecewise function. So let's take a look at one more with a piecewise function, and then we should be good to go, and let's do that on the next slide. Alright, so for this example, we've got a piecewise defined function, f of x, 4 minus x when x is less than 1, and 4x minus x squared when x is greater than 1, and our job is to find the limit as x approaches 1 of f of x. So you might be thinking, Krieger, I'm just going to go ahead and plug in 1, right? That's how we do limits. Great. Where do you plug in 1? If you take a look at this definition, I can plug in any number less than 1 into the top function. I can plug in any number greater than 1 into the bottom function. But where does 1 fit? 1 is not less than 1, and 1 is not greater than 1. There is no spot to plug in 1. It's not defined at 1. And so you can't just plug in 1. You can't just pick one of these to plug in. That's not the definition. You're not allowed to do that. So what we need to do is we need to look at the individual one-sided limits. And so I'll do those in the different colors as well. We're first going to take a look, and it doesn't matter which one you do first. We're going to look at the limit as x approaches 1 from the left, meaning we're going to look at numbers that are less than 1. Now for this, I still don't want to plug in. Sometimes we can and sometimes we can't. What we're going to do is we're just going to use a table. You know what? Let's plug it in, and then I'll show you the table as well. So if I just plug in 1 into numbers that are the function that I would use for numbers that are less than 1, which is the 4 minus x, then this would simply be 4 minus 1, which equals 3. That is the limit. Now you're saying, well, what about the other portion, the x squared, 4x minus x squared part? We don't care about that. We're only looking at the limit as x approaches 1 from the left. So that 4x minus x squared doesn't exist in my world because I'm only concerned about numbers less than 1. If I switch over to that function, then I would be looking at this other limit, the limit as x approaches 1 from the right. And that we can do also by simply plugging in that 1, because we're looking at numbers bigger than 1, and so that would be the 4x minus x squared. So 4 times 1 minus 1 squared, hey, that equals 3 as well. And so, because of our rule, since the limit as x approaches 1 from the left of our function f of x, since that's equal to the limit as x approaches 1 from the right, according to our definition on the last slide, then what that means that the limit as x approaches 1 of f of x must exist, and not only does it exist, but it's got to equal 3 because the left and right side both equal 3. So when you're dealing with piecewise and absolute value, this is how you need to tackle it. You need to look at the left and the right side. You can still plug in, there's nothing wrong with that, but if not, you can always fall back to a table and that will work as well. So, I've got some homework for you. Let's get that up here. All right, excuse me, poof, there is your homework happening on page 777, 5 through 14 all. You need to make sure you do those by hand. Now, the beginning parts there, 5, 6, 7, 8, they're just pictures, so there's not a lot of work you can do with that. I mean, they give you the equations, but you can look at the picture and figure it out. 9 through 14, you need to do by hand. That's where you're going to break them all apart. Same thing with 19 and 20 and 23 through 30. That's where you're going to do the stuff from the last video where you have to do some algebra to break them all apart. Make sure you do that. If you just use a table on those, you won't get credit. In fact, you don't want to do a table on any of these. You want to make sure and do them algebraically. Okay, and then 53 through 56 are one-sided limits. You can do them just like I did here. You're just plugging in to see if the limit exists from the left and the right side. You do not need to, and you shouldn't be doing tables on any of these. If you have questions, please feel free to send me a text. But otherwise, have yourself a great day, stay safe, and stay healthy.